Now in this video I'm going to go over an interesting problem I saw on Twitter. So it's a PDE of this form. So to tackle this we're going to use a change of variables, a few identities, and then reduce it down. So I'm going to rewrite this equation as e to the x, and then we do partial notation, so f sub y, e that, f of x equals ex plus y. First of all, I'm going to introduce a change of variable, so we're going to let epsilon equals to e to the minus x and eta equals to e to the minus y. Now, we're going to first tackle the right hand side of the problem, so we can write, I'll put this here, e to the x plus y as e to the x times e to the y. So this is just epsilon minus to the power minus 1 times eta to the power minus 1, and this is equal to epsilon eta to the power of minus 1, or more so 1 over epsilon eta. So that is the right hand side dealt with. Now the left hand side we need to let obviously epsilon up to 4 minus e to the minus x, eta equals e to the minus y. Now we need to work with the chain rule, so we say that f of x is equal to f of epsilon times epsilon of x plus f of eta times eta of x, and the same way for y, just changing the variables as x is equal to y, we get this. So we can say that in this case we have epsilon of x is equal to minus e to the minus x, and then we can also similarly say that epsilon of y is equal to 0, and then eta of x is equal to 0. Well, eta of y is equal to minus e of minus y. Okay, so now we've got this, we can say that f of x is f of epsilon times e of x, which is minus e to the power of minus x, plus f of eta times n of x, which is 0, so we're going to get rid of that. I'm going to put that there, so that is minus f of epsilon e to the minus x, and it can also be similarly reduced down to minus f of epsilon times epsilon itself. Same goes via symmetry for f of y. We can just put f of eta times eta. So we have our change of variables. So now we're going to substitute this in to the original equation. So we can say that minus is epsilon times f of x, which is this. So it's minus f epsilon times y. So that is f eta times eta plus e to the minus y, which is eta times f of x, which is minus f epsilon times epsilon, and this is like before 1 over epsilon eta. So we have minus epsilon eta f of eta minus I'm going to keep it the same, epsilon eta f of epsilon 1 over epsilon eta, and then dividing by minus epsilon eta, we get that f of eta plus f of epsilon is just 1 over epsilon squared eta squared. Now what we're going to do, we've got a function here of epsilon and eta. However, we're going to add a dummy variable and keep these constant. So we're going to fix these, but we're going to add a dummy variable, and this is going to be in the form of t. So we have g of t is equal to f of epsilon plus t eta plus t, and simply the chain rule of this, we get that f of epsilon plus t eta plus t is equal to, plus f of eta epsilon plus t eta plus t. And so this is simply equal to what we have up here, but with plus t. So we can say that g of t is equal to 1 minus epsilon plus t root squared plus eta plus t squared. Now I'm going to put that in red because that's quite important identity that we're going to come back to. Let's go to black again. Now, if you use the identity, so using the identity that 1 over t plus epsilon and then t plus eta, that equals 1 over epsilon minus eta times by 1 over t plus eta minus 1 over t plus epsilon. Now, this is a case for t plus epsilon, t plus eta. So we need to improve this for the derivative, or for the case of a squared at the bottom. So we're going to use the identity, the fact that minus 1 over epsilon minus eta squared is 1 over t plus eta squared plus 1 over t plus epsilon squared minus 2 over epsilon minus eta times 1 over t plus eta, if I can fit this in, plus 2 over epsilon minus eta, just zoom in so I can try and fit this in, 1 over t plus epsilon. Now, this has achieved two things. We've isolated t, so we've got it here, 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 and here. And we've also allowed, so this is g of t, of this. So, trivially, to find g of t, we just need to integrate g of t, which we can quite easily do with these, with this sort of fraction breakdown. So taking the derivative, we're going to keep the constant outside because it doesn't depend on t. We'll keep things that don't depend on t outside. We've got epsilon minus eta t, and this is just going to be what we have from before. So the integral of t plus eta minus 2 dt plus integral of t plus epsilon minus t dt. That's right. Yeah, so now we've got a constant here and a constant here. Then we take this outside. So this will be minus 2 epsilon minus eta to the integral of t plus eta minus 1 dt, and then finally on the last line plus t of epsilon eta and the integral of t plus epsilon to minus 1 dt. Now this is quite trivial integration that we probably did when you were about 16, 17. So we're going to simply integrate all this. So we get that this is equal to 1 minus 1 of t plus eta minus 1 over t plus epsilon minus 2 epsilon minus eta of ln of t plus eta, and then plus 2 over epsilon minus eta of ln t plus epsilon plus a c. Don't forget constant. Okay, so remember we have, if we go up, we've got a function. We've got this essentially. So I'm going to copy and paste this. This is what we've essentially found, or this is what we've turned our function into. So if you want to get, if we let t equal 0, work this out. If we let t equal 0, we get that t at 0 is equal to f of epsilon eta, which is what we want. So we're going to let t equal 0, and so this turns the equation above into 1 over eta minus epsilon minus eta squared, 1 over eta minus 1 over epsilon minus t over epsilon eta ln eta plus t over epsilon eta ln epsilon plus c. Hoping that makes sense. Hoping that's quite a simple step to follow. And so we can just clean this up. And so we get that the final solution is 1 over eta epsilon minus eta squared plus 1 over epsilon minus eta squared plus 2 over epsilon minus eta cubed. And then this is just log property, so we can do ln of eta epsilon plus c. And then we put it into red. This is our final form of the differential equation, so that is done.